Hi guys, I'm Petar and I'll be talking to you today about basic modeling principles that we employ in simulations in Typhoon Hill. So I hope you have a good time and have a very useful training. Okay. So this presentation is going to cover the basics of the modeling. So we're going to talk about the areas in which Typhoon Hill simulators are used. We're going to talk about some constraints of real-time simulations. Then we're going to talk about basic components in our existing library. We're going to move on to the processor architecture, and we're going to discuss how all of the components from the library are modeled to the processor. And lastly, we're going to discuss some additional features of the simulator, like switching losses, dead time violation detection, and digital input oversampling. So let's start with the basics. So the main application of Typhoon Hill systems today is in the field of real-time simulation of power electronics converters and microgrid plants. So first we're going to talk about the power electronics plants. They're highly nonlinear, mainly due to the presence of switching devices, and in typical converter topologies, switches are not only present in significant numbers, but they're also cross-coupled and operated at high frequencies. Today, it is not uncommon to have medium to high power converters switching at tens of kilohertz and running in fast control loops. So all of these requires very fine simulation resolution to properly model the dynamic behavior of the power plant. So as an example, we're going to have a look at back-to-back three-phase two-level converter. We can see that even such a relatively simple model has 24 switches in total, so 12 IGBTs and 12 diodes. And on the image to the right, we can see the typical inverter output voltage and output current waveforms, and it is clear that they're highly dynamic. On the other hand, if we move up to the system level and start speaking about microgrids or small-scale power system applications, traditionally we're talking about somewhat lower dynamics, but the sheer size of this model can make them very hard to solve. And today we see that more and more converter-based generators and loads are added to the grid. So we see that some microgrids are switching to DC distribution, and all of this requires very dynamic models. So today's microgrid models are not only relatively large, but they also cover a pretty wide range of dynamics. When modeling microgrid plants for hardware-in-the-loop testing, we are also interested in modeling certain control elements as well. Typically, we model primary controllers like converter controllers or protective relays. And they're usually interfaced with external controllers using some sort of field bus communication. So in addition to plant modeling, our Hill machines need to offer support for control modeling as well, and field bus communication protocols as well. So simulation of power electronics in microgrid plants is clearly not a trivial problem, and especially if we consider the constraints of the real-time simulations. So there are three main points to the constraints of real-time simulation. The first time is that our models have to run with a discrete time step and with a discrete and fixed time step. So we don't have the luxury to dynamically adjust the simulation time step and save some processing time this way. And since we have to run short simulation time steps, we have no time to use iterative solvers because we only have one try to find the right solution for the next step. The second point is that the available computational time for each step is strictly limited. So all the computations in any model, no matter how big or how small, need to be finished before the next simulation step starts. Otherwise, we'll get overruns and our simulation results will not be accurate. And the third point is especially important in power electronics skill applications. And the point is that we need to keep our simulation response time very short, and it needs to be comparable to the real-time power plant response. So what we mean by this is that the time from an event on a simulator input to the corresponding simulator response visible on its output needs to be as short as possible. And we refer to this as the look-back latency. Okay, so we're modeling complex power electronics and microgrid plants in real time with high fidelity. So how do we do it? Our solution to the problem is a so-called piecewise linear modeling approach. What do we mean by this? So for each switch state permutation, our circuit model is considered to be linear and time invariant. And as the switch permutation changes, so some switches open or closed, we simply switch to another linear and time invariant model. So our circuit is represented by a number of LTI models. We switch among dynamically based on switch states. So each switch permutation we call a mode of the circuit. So since the circuit modes are linear and time invariant, they can be represented in the states as a state space model. The state space matrices are easily discretized, and so our circuit is represented with a number of matrices where only one set of matrices is active at a time. So since our simulation time step is fixed and all the reachable modes are known beforehand, state space matrices can be calculated in advance and stored in the solver memory. So this way we can dramatically reduce the runtime computational load, which helps us achieve very short simulation time steps. However, there is a price we pay. So we can see that the number of modes or the state space matrices per circuit is 2 to the power of n, where n is the total number of switching elements. So we can see that the number of modes grows exponentially with the number of switches in the circuit, which puts very high strain on our memory resources. So for example, let's take a look at our two-level three-phase back-to-back converter. In total, here we have 6 switches in one converter and 6 switches in the other converter, considering the IGBT diode pairs as single switches. So the circuit from the image has in total 12 switching elements. So there are 2 to the power of 12 possible switching permutations. So this means that more than 4,000 state space matrices need to be stored in our device memory, and what's more, every additional switch would double this number. So it is clear that with this exponential growth, we cannot scale above a certain level of complexity with our models. Our solution to cope with this problem is to divide the complex circuits into multiple subcircuits in order to keep the number of modes on a manageable level. So each subcircuit is represented and calculated independently with its own mode set. So in order to make subcircuit behave as the original circuit, the one that was split, they need to share information, and this is done through the mechanism of variable exchange that we're going to cover later on. So let's go back to our back-to-back converter example, and we can see that if we split the model so that one converter is placed in one subcircuit and the other converter is placed in the other subcircuit, we can see that each of those subcircuits has a total of 64 nodes, so 64 modes. So overall, the original circuit, the total number of modes for the original circuit goes down from 4,096 to a total of 128. So we have effectively linearized the problem. So as a result, we have significantly reduced the memory footprint and added an option to parallelize the model execution. So with this approach, we are reducing the memory requirements by significantly reducing the overall number of modes, and we're also shortening simulation step by computing the smaller subcircuits in parallel. Moving on to the components of our schematic editor library, first up are the components that we actually use in circuit partitioning or dividing the larger circuit into multiple smaller subcircuits. So how do we do this? For now, we do this manually by using the so-called coupling elements, and you can see them depicted in this slide. So coupling elements are essentially ideal transformers which introduce one time step delay. So they are also asymmetrical, which is emphasized by the component icon. So you can see it is red and green, where red represents the current source side, while the green represents the voltage source side. So there are 2 types of coupling components: core coupling elements, which are used for partitioning of larger circuits among the cores of a single hill device, and device coupling elements, which are used to divide large circuits among different hill devices. So in one of the following presentations, we're only going to cover this circuit partitioning. Next up in our component categories are power electronics switching blocks. So our converter models are based on ideal switches, meaning that all switches modeled in a converter are 0 current when open and 0 voltage when closed. Power electronics converters are organized as highly optimized pre-packed blocks. So why do we use pre-packed blocks? It's for 2 reasons. So because this way we can really optimize them for real-time execution. So this means that we are able to utilize specialized runtime logic that can quickly and accurately calculate the correct switch states, which is rather straightforward for IGBTs, but less so for diodes. And on the other hand, we can reduce the total number of available modes by removing the redundant ones, but also the ones that are not of interest for a given topology. Contactors are implemented in a similar way. So they use one mode per contactor state regardless of the number of contacts. So even though a multi-phase contactor can be composed of single-phase ones, it is always recommended to use multi-phase ones if possible. They as well use the specialized runtime logic that allows accurate turn-on and turn-off delays, and in the case of single-phase contactors, a zero-cross turn-off function is available. So far we've explained how we model linear components in switches, but how about some nonlinear elements? So some examples of nonlinear elements, and you can see the images on the right, are the PV panel, the battery model, the saturable inductor, and the saturable transformer. So these kinds of components are modeled with the help of lookup tables. So as an example, we're going to talk about the battery model. So the battery model is represented by its discharge curve, where the battery voltage is a nonlinear function of the battery charge. This discharge curve is stored in the lookup table, and in the circuit the battery is represented by a controlled voltage source. So the current of the controlled source is measured and integrated to obtain the battery charge, which is used to read the corresponding voltage value from the lookup table, and that voltage value is fed to the voltage source. Similarly, the PV panel model is represented by its IV curve, and the IV curve is stored in the lookup table. In the circuit, the PV panel is represented by a current controlled source, and the voltage of the PV panel is measured, and its value is used to read the corresponding current value from the lookup table, which is then fed to the current source. Next up are machine models. So inside our component library, there are various electrical machine models, starting from induction machines and synchronous machines to permanent magnet and DC machines. All of them are implemented with the help of a dedicated machine solver. So similarly to battery and PV models, machine model consists of two parts, and you can see these parts on the image to the right. So on top is the electrical circuit part, here represented with some voltage and current measurements and controlled current sources. And the electrical part is used to interface the machine model with the circuit around it. The second part of the machine model is the actual machine solver, which is a dedicated hardware module that calculates electrical part of the machine model, the mechanical part of the machine model, and it also provides speed and position feedbacks in the simulation. So for some of the available machines, there are two circuit representations available, so current source models depicted here and the voltage behind reactance models. So up to now, we've only talked about electrical domain modeling, but how about modeling of control loops or some slower physical processes? So for this, we use the so-called signal processing components, like for example, gain, sum, integrators, accumulators, and so on. And they're easily recognizable. You can easily distinguish them from the electrical components by their blue color. So they're implemented using C code and are typically run at higher simulation time steps compared to the electrical components. Another category of components exists. So we've only talked about purely electrical or purely signal processing components. However, there is another category called hybrid components, which are composed of both electrical circuitry and the signal processing components. Some of the hybrid components in our library are various circuit breakers, RMS, voltage and current measurements, simplified engine generator, and the constant power load and source. So here on the image to the right, we can see the implementation block diagram of the implementation of the constant power load. So it also consists of an electrical circuit and signal processing based control. So the power load, constant power load, is represented by a current controlled source. Its voltage is measured and it's fed to the signal processing control, which in turn calculates the required current so that the active and reactive power references of the load are met under different conditions. So the newest addition to our component library are actually communication components. So in microgrid applications, the communication protocols are often used to connect real external controllers with modeled control elements. And communication protocols in Typhoon are implemented through specialized communication components. So their role is to connect internal signal processing components with external devices. With this, we have covered the very basics of our modeling and are now going to focus on explaining how our models are mapped to our simulator, and we're going to discuss the simulator architecture.